Kilroy says. Almost.
And I guess we are live now, guys. Let me turn this off so it doesn't blast you guys. Anyway, good morning, good afternoon, good evening, no matter where you are around the world. Welcome to Kilroy's World. Welcome to, I guess, the lecture for Module 3 tonight. We're going to talk about series, resistors, voltage drops, stuff like that. Answer any questions. Now, don't try to stump me because you might. Anyway, let me see. I see Leonard out there, and Edgar's also out there. And anyway, guys, I'm here. I'll just go ahead and start up. In front of me, right in. Let's see. I can't tell which way it is. Like right in there is the Module 3. I've got the labs as normal in the module. Or in the folder for the labs, and I'm going to go through these documents, which will be the ones I'll pass out and the ones that we'll go over tonight.
Ruben says, "Hello."
Hey, Ruben, how are you? Welcome. We've got a couple here, and I'm going to start up with this. You guys can follow along. Well, no, I guess you can't. Because the module is still closed. It'll open up on Monday. Even though Monday is Labor Day, you'll get access to it then. But on Tuesday and Thursday, I'll hand out the documents like I normally do. So let's go ahead and start with this. I guess it's going to open up a Word document. Let me drag it over. Should have opened it up right in there, but I've got the document here. I hope everybody's doing great tonight. This has been a long week, but we have all gotten through it, right? So first thing we're going to talk about is series resistance. And in the last lab, there were some experiments or some labs that included putting resistors in series and making some checks on current. This will just kind of reinforce it, and we'll go a little bit deeper into it. So just as for some review, the schematic is a drawing that represents the actual electrical circuit that you're putting together. And every component's got a different symbol, and you guys will see later on what some of the different symbols are. In fact, last time, we talked about switches and fuses and the different types of schematic symbols for those. So the resistor, the schematic for identification for a resistor, is this symbol that looks like a little jaggedy component with basically two leads on it, because a resistor, and I know I've got a resistor around here somewhere. A resistor has got, let's see, no, I know you guys know what a resistor looks like, but I'm bound to show one, and of course there's not one in here. How about that? Wait. Hey, there is a resistor right there. It looks like a little tube with two leads sticking out, and of course those two leads normally will sit down in the board. There's different sizes or different wattages of resistors. That one and that one. I think this one's a half watt resistor, and this one's a quarter watt resistor. Notice how much smaller they are. Guess you can see them. And of course, there's bigger resistors, way bigger. And I don't have any bigger ones. Not to confuse matters, but there's other components, and I don't have one here, that look like resistors that are actually diodes. They have, and you guys will probably see them later on. Actually, maybe not even in this class, but that's what a resistor looks like, right? And I know everyone knows what one looks like, but there it is for those that don't know what a resistor looks like. Okay, so onward. Like I said, there's many resistors in a circuit. I've got a circuit here. And there are a bunch of resistors. Okay, these. Let me see if I can get a little more light on this. Hope that helps. These right here are resistors. I'm just trying to see how well it shows up there. Tell you what, let me make this big. Oh, and I got the cam. So let's wait for this. So these, no, sorry, it's hard to point. These right here are resistors. These blue ones. They're actually standing up on edge. Normally they poke through. Let me see if I can get that to focus real quick. There's something else on the boards. They'll have an R like in the upper left-hand corner, I guess. R10, R11, R22, R23. See, those are all standing up. One side of the resistor is going through the board, and the other one is just kind of coming right around and coming back down. And I probably should have made a different scene for this so that I wouldn't have to be messing around with this right here. Let me do that. Let me duplicate that. We'll call it and we'll make it big so you guys can see the actually so I can show you guys stuff as I need to, right? And then I just flip a little button and like magic we go back to the way we were. Woohoo! So going back up here, there are many resistors in a circuit. To distinguish one resistor from another, a number is added to the identification. That's what I showed you on the board. In this case, they're showing R1, R2, R3. How many ever resistors? Normally, you label them or mark them on a board from 1 to whatever. I mean, you don't have to do that, but it just makes sense, to do it that way. And usually in order from left to right, top to bottom, just like we read. So if you are looking for a resistor on a physical paper schematic, you kind of might have an idea. If there's R3 over here and you're looking for 5, well, it's going to be close. That doesn't always happen that way, okay? I've found resistors in all sorts of places sometimes. And
says, greetings programs.
Hello, Trey. How are you?
Max World Entertainment.
Max World Entertainment out there.
Oops, I forgot school is in.
No problem at all. No problem at all. It's a lecture for the next class. It's totally okay, guys. If you want to have some fun, if you want to see some cool Star Trek fan films, go subscribe to Max World. It is awesome. It is the best. One of the best. Let me say it that way. It's the best that I've found in a while. But anyway, I'm certainly enjoying it. And as you guys know, I am a Star Trek fan. Gee, you wouldn't know that, right? You wouldn't know that by the company I keep, right? But anyway, some of you don't know that, I guess. So back to the resistors. The resistors come in different ohmage or different values of resistance. Normally on a schematic, when you see a resistor, it'll have the number for the resistor, or the component number, and it'll also have the value. And as I always harp, you always have to put a label what you're looking at.
Thank you so very much, my brother, for the shout out. I am so very humbled, sir. Thank you.
It is I that's honored indeed and humbled. The values, as I always harp, are put that value down, right? Well, you have to know what it is, because if you go check it, or if you go, do a calculation, you have to know what it is. This one is like a 1K ohm resistor. This one is a 3K ohm resistor. Likewise, a 5K ohm resistor. It could have said 5,000 ohms. It could have said 3,000 ohms. But see, always use a label, and what size of label. In this case, K, which is 10 to the third, which is times 1,000. So that being a 5,000 K. I bet there's a lot of resistors, or do they have resistors in the Star Trek universe? I've never heard anybody talk about resistors. But I bet when Spock is up underneath the control panel there, or one of the stations, I bet he's bypassing resistors, or who knows? I don't know. But it's just part of the circuit. So in series, the term series means that the components are connected, or how they're connected. And in the case of series, the components are connected basically end to end, like so, right? I mean, obviously you're not going to connect them like that. They'll be connected more. Yeah, let me borrow this here. They'll be connected more like this. Let me see if I can clear this off some. Let me drop. Let's see. Let's drop this down to where? To right there, I guess. Let me flip back the scene.
Says, no, because resistance is futile.
Resistance is futile, yes. I was waiting for somebody to say that, too. So resistors in series, though, they connect to each other like this. So, because we know that this line right here has continuity, well, we're gonna actually put it in there. This is a little thicker, and bring it down. So now between here and here, let me get these wires out. We don't need them to. We don't need these stinking wires. So between here and here, we have a series circuit. And in the last lab, you guys worked on multiple of these, which you were working with series circuits, or series resistors. So this resistor is in series with that one, because there's continuity between here and here. How do I know? The way I know is if we, let's see, can I do this? Let's see, where's the camera at? If we do this test here, and let's see, is this meter on resistance, on ohms? Yes, it is. It is on the ohm scale, which is this one here, and it happens to be between the 200K and 20K range. I never noticed that there wasn't a number there, but that's a range, I guess. Don't know what the range is. See, that's why you always have to label stuff, right? So in this case, I'm trying to get this. So we've got continuity on our meter. Close enough. Let's go to 200K. I don't know what these resistors are off the top of my head. So we've got zero continuity there. We've got the value of this resistor here, which if that's 200K, then that's 0.3. Let's go back. 0.3K. There's a 20K. There's a 2,000. Oh, there's a 2,000 range. I'm on 2,000 range right now. Ooh. It's only saying 2 ohms. That's okay. But if we look at this is 322 ohms. And let's see what this one is. Oh, this one's overloading, or going above the range. Let's put it to the next range. This one's like, that almost look like 10K is what I'm gonna. No, wait, it was on a 20K. It's on 20K there, so it's more than 20K. I don't know what that range is, to be honest. This is the 200K range, and we've got 9.9K. So is that 100K? In any case, no matter how many Ks that range is, it's still 9K or 9,000 ohms. So the resistance in series in this thing is going to be between here and here, and it's basically the addition of this resistance and that resistance, and we'll get more into it here in a second. So let's go and see. There's, let me go back to the other scene. There's a, that's a little big because it is a blocking. It's a blocking. Let's see. Yeah, there we go. That's probably okay there. So here the two resistors are connected in series, and that's a schematic view, or the schematic. I guess you probably want to see me. No, maybe not. There's the schematic view of not necessarily those specific resistors there, because the values are different than this, but what it would look like. And then if we connected three of them, it would look like this. And move this over. Yeah, this could stand to be just a little bit smaller. If we had three resistors connected in series, then it would be like that. And you guys used three resistors last time also. Now, there's something called total resistance, or what's called R sub T. You'll refer it, or you'll hear me referring it to as R sub T, or RT, or total resistance. And that's the resistance that when we connect the ohm meter to the ends of those resistors, that's the resistance we get, which is what I was showing you for those two resistances there. And it has a formula, like everything in this world. And by the way, you might not have to write this one down because it's real easy. Total resistance, R total, and it sometimes will be one way, sometimes be other, but it still means the same thing. Total resistance has a formula of R1 plus R2 plus R3 plus ... right? Which means that any resistor that's placed after that, you basically sum up those values, and that gives you the total resistance. And it makes sense if you think about it. You know, it's what is the resistance down that circuit through all those resistors. And it's used to indicate that the resistors are placed in series. The total resistance, again, is the sum of the values of the resistors. And it's, I was going to say, it's usually the measured resistance, but it could be the calculated resistance. In other words, according to the stripes on the resistors, you know, what's the value. But when we're talking about calculations, we're going to want to measure it anyway. So usually it's the measured value of that circuit. So really, that's all there is when we say a series, you know, resistors in series. They're just one right after the other. So let me go ahead and close this down and go back over to Blackboard. And I think this one was next. I'm going to have to probably, yeah, I think so. Let me look at this other one though. I'm trying to keep them in order. Yeah, I guess I'll talk about this one. Let's see. No, I'll set it aside and I'll go back to this right here. So talking about series circuits again, the term series describes items that are one right after the other. And this says if you take two 50-foot or 50 foot water hoses and you connect them, one right after the other. That 100-foot string of water hoses is 2 water hoses in series. Basically, the same thing with lights. If these are LEDs, you can have 2 LEDs in series, and the current is going to go into one lamp or LED or light, and travel through the filament that's in the lamp and out the other side, and then over to the next bulb or light or LED, and up through that filament, and then back down out the other side. Those lamps are in series. A lot of stuff can be in series. Kind of like a Christmas tree lighting. Sometimes those bulbs on the less expensive ones, they wire them to where those bulbs are in series. So that's why when you put them away for Christmas and you pull them out the next year, and maybe somebody has stepped on a bulb, or a bulb has gone bad, and they stepped on it and broke the bulb, that string might not work, or part of it might work. It's because those bulbs are wired in series, and that's one bad reason to or one of the reasons that if you wire stuff in series, if one of them goes out, the other one goes out too, or the other 20 in the case of a Christmas tree light string. So they have pluses. They save money on wiring. They save money to in the way it's hooked up and stuff. So there are pluses and negatives to it. So the resistance, for instance, of 2 resistors that are connected in series, notice that you can distinguish between the 2 resistors. They're labeled R1, R2. They both have a value. And to measure the resistance, like I spoke of earlier, you just take and let me move this over here. Yeah, you just take and put the ohm meter, and it doesn't matter which one you put on. There's not really a polarity, at least at this point. We'll talk about polarities later. At one point, or at point A, and at point B, and that's how you measure the resistance. Can anybody want to guess how much resistance is there? Remember, total resistance is the resistor is R1 plus R2, right? It's even in front of us, right? Excuse me. Of course, it's 200 ohms, right? Whether you calculate it as being R1 plus R2, or just go, hey, it's R1 plus R2, 200 ohms resistance, and that's what the ohm meter would give us.
Says 200 ohms.
Yes, Ruben, you got it. 200 ohms. I actually just heard the bot. I've got a bot here in my ear. And it's actually saying what you guys are saying, and there's a slight bit of a delay. I didn't realize it was that long, but yeah, exactly 200, Ruben. And likewise the bottom one, and I'm asking this, what about this one? It's got 3 resistors, right, in series. Technically you should just be able to answer it, right? And if I ask you, what's the resistance? Obviously, it's right there. But yeah, it's R1 plus R2 plus R3, which is 300 ohms, right? Where this will matter, where I will be checking, is when we're doing the labs and stuff, right? And you the last lab that we did, where we were using the resistors, we defined the resistors, we found the nominal values of the resistors, or we calculated the nominal values of the resistors, so we found the actual value of the resistors, then we added up the nominal values, and of course nominal value is what the bands say that the resistor is, without looking at the tolerances. And then when we put it down in the circuit, now we're working with those tolerances. We don't really know what the values are unless we measure each individual resistor like you guys did, and then you add those. But they were also in series, and that's why they always added up to whichever ones were being connected. You know, resistor 1 and 2, resistor 2 and 3, resistor 3, 4, and 5. I think you guys know if you did the lab. The formula shows below R1 plus R2 plus R3 equals R total, or R sub T, or total resistance. So when resistors are placed in series, the total resistance is equal to the sum of the individual values. The formula below shows what it is: R1 plus R2 plus R3 plus ... which is equal to the total resistance. Now you say, well, what about voltage? Well, what about current? Well, according to Ohm's law, it's that triangle relationship that we spoke about last time. Let me bring it up. Let me bring one up, and maybe I probably can go over here and find it and actually add it in. So let me add a source, and I'm going to add an image because it was an image. Let me see if I can go find it. Let me create a new image. Let's call it Ohm's law triangle. And let me go find it in my files. Just give me a second here. It's over in here. There it is. I wonder why. Oh, I know why. This is the one I use for a thumbnail. So there is Ohm's law. That is the Ohm's law triangle. I guess that's good enough place. So if you notice, the current of the circuit shown is 100 milliamps. Okay, so how did we find that out? Well, like I was saying last time, if we cover up, I wish I could cover up, I guess, I don't know, that's probably on my end. If we cover up the I, in other words, the voltage divided by current, or voltage divided resistance, but in this case, we're trying to find current, so we cover up the I, and we see that current is equal to voltage divided by resistance, as you guys, I think, have also done. But again, we're just going over this stuff as a little review. The voltage here is the source voltage, which in this case, it's kind of looks like a battery. It could be a battery, it could be some other source of voltage, but it's 10 volts. And notice how I'm saying this, it's 10 volts. Now, it is a whole volt, 10 whole volts. And even though they don't have it here, shame on them, I do know that this is 10 volts divided by the resistance in the circuit, which is 100 ohms, and that really should have ohms behind it, so we know. But if we look at that, this is whole. This is whole, meaning not fractional, not millivolts, whole volts divided by whole ohms or resistance, and that gives us whole amps. So those whole amps, the calculation comes up to 0.1 amp, which when we convert it over to milliamps, that is 100 milliamps. Thus, how we get 100 milliamps. So the current flowing through the circuit, going through the resistor, back into the battery, that current in there is 100 milliamps. We'll go on. So when two or more resistors are connected in series, the current of the circuit can be found by using the total resistance. So then you've got two resistors, but the thought is, okay, so what's the total resistance in that circuit? Because as the current is going through the circuit, we pop another resistor in there, it's going to limit the current more because it's in series. It's going to add to the existing resistance that's there, thus R1 plus R2, and we got more resistors or more resistance. So in this case, it's the current going through this circuit here is the volts divided by the total resistance. It states total resistance, but we're talking about resistance in general, right? So looking at our formula again over there, if we look at it, again, it's voltage divided by resistance. Voltage is 10 amps. 10 volts divided by, now it's 200 ohms. So now the current is now 0.05 amps. Whole volts, whole ohms, whole amps, right? Even though the number is fractional, it's still, the label is still amp, which in this case is 50 amps, or 50 milliamps, excuse me. So comparing this circuit that has 200 ohms to this circuit that has 100 ohms, notice that putting in an extra resistor actually cut the current in half. Now it's the same resistance, so it works really, really nicely that way. So the more resistance you have in the circuit, the lower the current's going to be. So, I mean, it's doing its job. A resistor resists current, right? So the current is now being limited even more because we added another resistor in there. So over here, the schematic symbol for DC voltage is shown, and it's kind of shown, let me see, from the point A is positive and point B is negative, and this would represent voltage from a power supply. Because, we talked about we can have it from a battery, we can have it from a power supply also. So how do I know? How do I keep track of which one of these is positive and negative? You guys got an idea? Can you guys maybe figure out a way so that I can remember which side is positive and which side is negative? Point A is positive, point B is negative. But looking at that schematic symbol, I'm trying to highlight it, I guess I can't. Looking at that schematic symbol, how do I know which one, how do I remember which one is negative and which one is positive? I'll give you guys a couple of seconds because I know there is a delay. But that's something that we probably need to remember really well, really well. Take a guess. Look at something else. By the way, if you're in the channel, and I'm cheating, I'm looking at those, or if you're in the channel and you want to say hi, by all means, say hi. If you have a question, by all means, ask a question.
Edgar M. says, positive has a bigger line.
Bingo. Positive has a bigger line. Exactly. Now, let me even reinforce that. Think of it this way also. The negative one, the negative side, looks like the little one, like a little negative symbol. So, I mean, either way is totally correct. You can say the bigger one is the positive. Look at the negative. The negative actually looks like the negative sign because it's just a little dash, even though the top one is a dash too. But so use the combination of both. The bigger one is the positive because we want to be positive. We want to be real big. I mean, I don't know, however you want to remember it. That's kind of exactly the point. How do you remember it? That's the thing. And there's no right or wrong. It's how you remember it. So that's how I remember a DC voltage or a voltage source. And it kind of looks like a battery too if you look at it. It has plus, minus, plus, minus. So batteries, like if you put two batteries together, they would have a positive pole, a negative pole, and then it's hooked up to a positive pole, and it's hooked up to a negative pole. So that's what the lines actually really mean. It kind of looks like a battery too. I mean, it is a battery also, but in this case, it's a DC voltage source. So the schematic symbol for resistor again is the little squiggly line with the resistor number and the value. the voltage source is usually going to have, some type of label also showing the voltage on it. Down here, if you notice, let's see, the circuit shown in Figure 6.1 is drawn. Trying to get it centered in here. The circuit shown in Figure 6.5 is drawn schematically correct and shown in 6.6. So we've got two resistors, again with resistor numbers and values, and a source and value. And then if you notice the red lines, those red lines are conductors that connect those resistors. Now, they could be the clads on a circuit board, the little lines that are down here. It could be the little lines. It could be wires that we use in in a breadboard. It could be those also. But the point is that let me turn off my meter. The point is that's a complete circuit. It goes from the positive all the way to the negative as a complete circuit. If this piece was missing here, then it wouldn't be a complete circuit. And actually, no current would flow through the circuit, and no work would be done. No LEDs would be lit. No resistors would heat up. Yeah, because the resistors heat up because they resist current. That's why the different sizes, they give heat off. Now, it's not a lot of heat. If you run a lot of current through it, though, by golly, it'll burn your fingers. Remember we were talking about a hairdryer and the resistance in a hairdryer? Remember we were talking about it was, 9.6 volts we calculated it to? Well, what happens there? It heats up, right? So that's a resistor. It just happens to be a heating element, but it's the same thing. It's a resistive element that limits the current. Now, in that case, it doesn't limit it a lot, so there's a lot of current flowing. Therefore, there's a lot of power. Remember, power is PIE. Power is equal to current times voltage. So the more current we have, the more power we're going to have also. Just a little side note. Okay, let's see something. Let's see. So let me make this a little smaller. I wish I could go. Yeah, that'll work. That'll work. I want to get it here. So here's some current examples. So to determine the current, and we did this last time too, but to determine the current of the circuit shown in Figure 6.7, find the total resistance. So what's the total resistance? Well, if we do R1 plus R2, hey, that's 300 ohms. So R1 plus R2 is our total, which is equal to 100 ohms plus 200 ohms. That is 300 ohms. So finding the current, it's 10 volts divided by 300 ohms, which in this case happens to be 33 milliamps. And they did the conversion automatically, but of course that would be 0.033 amps when you do the calculation on your calculator, because these are whole volts and these are whole ohms. It even says it, volts and ohms. So that's what I was talking about earlier. They didn't put those labels in there. And they did the calculation for us automatically. That should have been 0.033 amps, which we in turn would have converted to 0.033 milliamps. So to determine the current in this circuit, we find the total resistance. Gee, that seems to be a theme, right? We have to find the total resistance. The total resistance of R1 plus R2, or the total resistance is R1 plus R2, 1 k ohm plus 5 k ohm. No, I'm sorry, 500 ohms. 1 k ohm plus 500 ohms is equal to 1,500 ohms, because 1 k ohm is 1,000 ohms. So 1,000 ohms plus 500 ohms is 1,500 ohms. And of course, we still have 10 volts. So finding the current, it's 10 volts divided by 1,500 ohms. Again, whole volts divided by whole ohms. And it's 6.6 milliamps. And if you do the calculation on a calculator, it becomes this formula, 10 divided by 1500 is 0.0066. Try it if you don't believe me, which is 6.6 milliamps. See what we got. So let's determine the current of the circuit shown in figure 6.9. So find the total resistance. Total resistance is 3.4K ohms plus 5.9K ohms, which in this case, it shows it to be 9.3K ohms. Going back to the formula, 10 volts divided by 9,300 ohms is equal to 0.00107. But in this case, they've already done the conversion from amps to milliamps, and it is 1.07 milliamps. So yeah, so if you were looking at this as an amp, you would actually move the decimal 3 to the left, which would make it 0.00107 amps. That's why I keep kind of going back and forth. You should be able to do that calculation in your head automatically. And had I done this myself, this was already made up. I would have probably done or shown it in amps, and then which is equal to milliamps. But I speak it and I don't show it, right? Or I didn't show it. So the source voltage supply current to the total resistance. The source voltage supplies, I can't read. The source voltage supplies current to the total resistance. In figure 6.9, the voltage source is supplying current to 9,300 ohms. When resistors are connected in series and connected to a voltage source, current from the power supply is found by using total resistance, which is basically what we've been talking about. And I'm going to mention something else too. Some of this voltage I guess we don't have just one, do we? Yeah, so you see how here the voltage drops 10 volts here and 0 volts here, but anyway, there's a potential of 10 volts across this one resistor. When you have a resistor in series connected to a voltage source, or two resistors in series connected to a voltage source, this voltage source will, in this case, drop some of the voltage across this resistor. You can actually take a meter and check the value, and then some of it will be dropped on the other one. Okay, there will actually be a voltage generated on one resistor on R1 and a voltage generated on R2 if you take a measurement. Now, because both these resistors are the same value, technically, right? I mean, we're saying they're 100, but in real life they're not. But technically, they're the same value. You would have 5 volts being able to be measured on one resistor, and you turn around and 5 volts would be measured on the other one. Now, because you know that the tolerances in the resistors change the resistance value just a little bit, that value might be a little higher on one than on the other, but technically it should split up the voltage on those two resistors. If we have 3 resistors, see, this would be 100, so it would split up voltage across there. Let me talk about 2 resistors of different values. The ratio of the resistors, and we'll talk about this in the next one. Some of the voltage is going to drop on here, and more of the voltage is going to drop on here. You'll see that here in a second. So I think that concludes this sheet, or this part of the lecture on series circuits. So let me see what we got. We got a gray screen. We've got, see, we did that one. This is the one we just did, I think, right? Yeah, we just did that one. So let's go to the third one then. which is the one that I was showing you, or that I was looking at. So just as a summary, and this is kind of what I was saying earlier, and I think it'll show it in the last one. So some formulas to think about in a series circuit, and maybe this one needed to be at the end. Yeah, I think I'm going to leave that one for the end. Let me do this one. Let's talk about voltage drop, since that's what I started talking about, and then we'll come back to the summary. That probably makes a little more sense. So looking at series circuits, and I hope I got the right one. The current is the same throughout the circuit. Like you can see here, the current going through this circuit, if we take, this is an amp meter, and we're measuring the current. We break the circuit, we put the meter in there, and we're measuring the current that's flowing through here. Okay. Each one of the resistors contributes to containing or resisting the current. So let's see. As I'm talking, can somebody calculate the total resistance of the circuit? Basically, it's just adding up the circuit, if you guys wouldn't mind. So the total current leaving the power supply is 17.5 or 18 milliamps. The current is flowing through R1, R2, R3, R4. The same current, calling it 18 milliamps, that same current is flowing through there. It's 18 milliamps here through this resistor, 18 milliamps here, 18 milliamps here, 18 milliamps here, and it comes back to the voltage source. There's what I was talking about, voltage drop. Now, I'll show you how to calculate the current here in a second. Yes?
Says 285 ohms.
285 ohms. I bet you're right. And is that shown anywhere there? And yeah, if you just add them up, that's what you've got. So 285 ohms. I'm gonna write that down so I don't forget it. So it's probably going to be a really important number. 285 ohms. Good. Thanks, Ruben. So the voltage drop, as Ohm's law states, and let me make this to where I can see what we're doing, guys. As Ohm's law states, right? The voltage drop, voltage is current times resistance. So current, which is, what did we say, 18 milliamps? Or as it's showing it, 0.018 amps, right? The current times the resistance is 285, so multiply that out. What's the current times the resistance come to? And I'll do it on my end too. Counting for lag, we'll just kind of piddle here, and let's see, I got a calculator. Maybe I got a calculator. Yeah, there's my calculator, guys. It looks like a TI calculator back in the day. So 285 ohms times, now because they're whole ohms, I'm going to convert it from 18 milliamps, right, to amps. And actually this right here is showing amps. It's not showing 0.018 milliamps, it's showing 0.018 amps. So 285 ohms times 0.018 amps gives us 5.13 volts. Now, if you look at the circuit, it's saying, hey, the circuit's 5 volts. But if you actually look at it, that's pretty darn close. So whatever that current was that was flowing through here, which was 0.018, and And that resistance tells us what the voltage drop is. And really what the voltage drop is at this point and this point, which is what's connected to the battery. Now I'm going to do something else. I'm going to take, excuse me, wash that down. I'm going to take and do it with 0.0175, which is 17.5 milliamps. It rounded it up to 18, right? Times 285 volts. And that comes out to 4.987, which is a lot closer to 5 volts, right? So really the current, when we rounded it up, it kind of threw our calculation off, but that's okay because it was close enough too. So that voltage drop across the whole circuit at this point and at this point is this voltage drop here. And we know it because it says that it's 5 volts there, but we could calculate that voltage drop just like we did. So in the circuit above, 17.5 milliamps of current flows through the 220 ohm resistor. Multiplying, so it goes through here. The 220 is right here. So current is going through here. So we've got 17, I wish I could bring that down so you can see it. So anyway, so we've got 17.5 milliamps or 0.0175 amps of current flowing through the 220 ohm resistor. So multiplying 0.0175 amps by 220, we get 3.86 volts. Voltmeter placed across that 220 ohm resistor like that would show what's called a voltage drop of 3.86 volts. So the voltage across the 220 ohm resistor, which is called voltage drop, that voltage dropped across that resistor is 3.86 ohms, which is pretty cool, right? If the current of the resistor and the resistor value is known, then the voltage dropped across the resistor can be calculated. Let me say that again. So if you know what the total current, now this is for a series circuit, if you know what the total current, or if you know what the current that's flowing through that resistor is, and you know what the value of the resistor, hey, all you need is two out of the 3 to find the third one according to Ohm's law. If you know voltage and if you know current and if you know resistance, you take the current, you multiply it by resistance, and that gives you the voltage drop across that resistor. So now, how would you figure out the other voltage drops across the other resistors? You basically would do the same thing. You would multiply the current going through the resistor and the value of the resistor, and that gives you the voltage drop. You see what else it says here. So now let's look at this one here. If we have, and I'm going to make some quick calculations. So calculate the current, which is 0.0175 times, and I can't really show this to you very well, times 10 ohms. That's the voltage drop across R1. And then if we do 0.0175 times 22 ohms, and I'll show you this. That's the voltage drop over R2, R1, R2. Maybe I should have some type of little whiteboard thing that I could do. I think I got an idea. In fact, I probably could do it right here. How about that? No? Oh, wait, let's enable editing. Yeah, I could do it right here. Let's go down to this, to where we were. So what I was doing is, for this resistor here, ooh, this is going to get fancy. Oh, check this out, guys. Let's do it this way. So for this resistor right here, let me see. Yeah, but I'm not going to be able to do that. It's going to, maybe, let's see. I'm going to type, let's see, 0.01 0.75, yeah, times that. We could use this if we wanted to. Yeah, why not? Let's use that. I always like to use this right here for multiplication. But either one. So let's just say times 10 ohms.
Ruben Ricane.
Yes.
Says. R118 VR2 396 VR3 594 VR4 396 V.
Sweet. So, yeah, for some reason I'm not seeing the chat in my software, but I know that it's coming through because I can hear it. All right, so you're saying that resistor 1, let's see something here. So you're saying resistor 1 has a voltage drop of 18 volts, and resistor 2 has a voltage drop of 396 volts, and resistor 3 is 594 volts? Or do you have points in there? Ah, there are points. 0.18, 0.396, 0.594, and then 3.96. All right, so yeah, and you used 18. So tell you what, I'll go ahead and use 18 also. I don't think the 5 volts will come up exact, but let's come on. 0.18. 0.18 times 10 is 0.18. And of course, where did it go? Yeah, this ain't going to work too well. There's that. Yeah, it's going down to the bottom. Oh, there it is. So the next one is 22. Whoops. 22 ohms. No. Let's do 0.018. You know, I'm really tempted to do 0.17, and then we'll compare the values. What was it, 0.175? What did it say? Yeah, 0.0175. 0.0175 times that is 0.175, right? And then you'll see where I'm going with this. 175 times 22. And that is, I'm just going to multiply it so that I don't mess it up. 0.0175 times 22, and that is 0.0385. What did you come up with? So you came up with 0.396, but that's okay. And then I'm going to do 0.175 times the next resistor, which is 33. So 0.0175 times 33, that is 0.577, right? Because you came up with 0.594. Oh, need a little equal sign there. All right, then the next one is 0.0175 times 220. I think we calculated that one. 0.01, 0.01. I keep hitting the wrong button. 0.0175 times 220. And that one comes up to 3.74, right? 3.74. You got 3.96. And that's correct because you used 0.18, or used, yeah, right? Yes, you did. You used 0.018. So adding those up, add yours up, Ruben. What do all those voltages come out to be? And I will add this up. I'm going to add 3.
Ruben Ricane
3.74
says
plus
0.175 times 22 should be 385.
Ooh, yeah. Yeah, no zero there. No zero there. Good, because that would have messed up the calculation. The 220 is 3.74 plus 0.577 plus 0.3. Oh, I think I just messed this up. Let's do this again. I'll start from the top. 0.01. Oh no, not 0. 0.175 plus 0.385 plus 0.577 plus 3.74 equals 4.8. Now,
Ruben Ricane.
What did you get for yours?
Mine equals 513V.
513, yeah. So it's close. It's not perfect, but it's close. So that current is there's probably more digits in that current, and this one's showing 18. Yours is showing, yours showed 18. Mine was showing 17.5. It's probably somewhere in between there. If we took the total resistance, let me look at this. If we took and we said, okay, the total resistance that we've got is what was it? 285, right? 285. So if we take the voltage and divide it by the current, 285 divided by by resistance, 5 volts divided by 285, that gives us actually, and this is the reason why. Oh, and I can't see. Let me switch this over. Let me show you this. This is the reason why those numbers. See that? When I calculated 5 divided by 285, it actually comes up to 0.017543859649112. So what's actually happening is we've got rounding errors that are in there. If we multiplied those values of resistors times this number right here, we would actually come up with 5 volts, as close as we could get to 5 volts. So that's why when you did it, or when you calculated it with 0.18 or 0.018, and I did it with 0.0175, I came up short and you came up long, because the number was actually somewhere in between. So I hope you understand that. But it actually mathematically, all the values will become the source value. There's that law that says that you can either create or destroy matter or energy. You always, whatever you've got, it's either changed into something else, but it's always there. So those voltages are accumulated, and as you can see here, okay, see it's saying 175 millivolts plus 386 millivolts plus 579. What did I get? Oh, it's up there. Is it 579? 3.86. What did I get? See, I got 374. You got, what did you get? Just want to look at the bigger one. Come on. Yeah, so you had 3.96, but in essence, it's saying our voltages were actually those right there. I think what it is because, yeah, see, this is amps rounded up. Anyway, let's just go back to this. So back to voltage drop. Ohm's law states the resistor value is known and the current value is known. Then voltage can be found by multiplying the two. And I want to stress that that's why you shouldn't round. You should use the raw number that you get from the from the calculator when you're calculating this stuff. So current times resistance is equal to voltage. Basic Ohm's law, right? In the circuit above, 17.5 milliamps of current flows through the 220 ohm resistor. So multiplying 0.0175 amps by 220 gives us 3.86 volts. You had 0.385. Is that right? Or is that what I got? Or is it fudging with us? Let's see. Let me multiply this. 0.0175 times 220. It comes up to 385. See, and even that's saying 386. This is saying 385. I think this is rounding it down too. But if we take a voltmeter and we put it across a 220 ohm resistor, we'll measure that voltage. Or actually, what we'll measure is we'll measure the actual voltage drop that's on there, because it probably won't be a 220 ohm resistor. It might be 223 ohms, 224 ohms. It might be 218 ohms. You know, whatever that that tolerance is.
It's fudging its numbers to make it even.
Yeah, exactly. It's rounding it. Yes, it is. So yeah. So as long as we get past that, we're good with that. And then remember what I just said. You can look at the resistor, and the resistor says it's 220 ohms, but we're measuring it as being 223 ohms. That's going to change the calculation too. And then depending on how many numbers you use past that decimal point, how accurate you are with those numbers is how you'll get a more exact answer. So just keep that in mind. But yeah, exactly. So if the current of the resistor and the resistor value is known, then the voltage dropped across the resistor can be calculated. We've said that before. We can measure it and we can calculate it, basically. At least close enough, right? I mean, because when you're talking about, half a millivolt, it doesn't really matter. Unless you're like using that voltage to calculate some, orbital path, and you're going at warp factor 4, and it's kind of like you need to make sure those tolerances are not absorbed in round up and round down. Excuse me. So in the circuit below, the voltage dropped across each resistor is shown. So the voltage dropped across each resistor is found by multiplying the value of the resistor by the current flowing through it. And now let's see, notice the sum of all voltages equals the source voltage, as we've kind of walked through and talked about. So here 10 ohms times 0.0175 amps is that many volts. It's 175 millivolts, but what we did is what it's doing, right or wrong. I'm almost tempted to add all those values up to see if it's actually 5 volts, but it should be, depending on the accuracy that those calculations were done at. So for solving for voltage drop, the current of a series circuit is found by finding the total resistance. So we have to make sure we know what the total resistance is of that circuit, and then treating this value as if it were one value. So whatever those values are in series is what we're saying that the one resistor is going to be. And then we know the voltage, we know the total resistance. So of course, as voltage divided by resistance gives us the current flowing through the circuit. And in this case, it's 10 volts divided by 1470 ohms. That gives us 6.8 milliamps, or 0.0068 amps. 6.805 milliamps. Look at this. This actually shows half a milliamp, or I'm sorry, not a half a milliamp, but a thousandth of a milliamp, 5 thousandths of a milliamp, because it's 6.805 milliamps. So this actually went even further as far as accuracy goes, even though it's saying, hey, 6.8 amps. So that'll throw numbers off. Now, as long as the numbers aren't really, really bad off, it's okay. So the current flowing out of the power supply is 6.8 milliamps. So through here, 6.8 milliamps, even though it's saying 6.805 milliamps. Then that's multiplied by the resistance. Then we know what the voltage drop is. We've got 0.68 volts on this one. We got 1.497 on this one, because we're multiplying 6.8 milliamps times 220 ohms. That gives us 1.497 volts. On this one, we've got 470 ohms. The total current is 6.8 milliamps. We got 3.197 volts on that one, and this one down here being 680 ohms. We've got 4.626. Some things to note: the smaller the resistor's value, the smaller the voltage drop will be. The larger the resistor's value, the larger the voltage value will be. So if this down here were a 10 mega ohm resistor, I would venture to say that pretty much all of that 10 volts was going to be dropped on that resistor, just like this being the biggest resistors, the biggest resistor in that series circuit. And notice too that it's kind of, because of the mathematical formula of Ohm's law, it's kind of a ratio of it. The smaller it goes, the smaller the voltage goes, even though the current obviously is the same. So that's something to note. That's how you know your values are going to be right if you're doing a calculation with voltage drops. Well, how big a resistor is it? And that's why when two resistors of the same value are on a circuit, you're going to get half the value on one and half the value of the other of the source voltage. So remember, an ammeter is placed in series with the circuit, and a voltmeter is connected across the resistor, as it's shown there. An ammeter is connected in the circuit, and a voltmeter is connected on top of it, basically, or across it. The proper meter set up to measure voltage. This is a really good point. Current and resistance is really important. So if you don't set them right, you might mess up the meter. So you got to make sure that if you're measuring milliamps, that you put it on a milliamp scale or an amp scale or whatever for amperage. If you're measuring resistance, make sure that it's resistance. And if for voltage, of course, you need to make sure that it's set for voltage. And if you have it set on resistance or ohms on the meter, and you go check voltage, you might blow the meter up. So you have to make sure. Okay, that's that one. And I think, let's see what else we got. Let's go back. I guess I could just back up, right? Which one did I do? This was the series summary, which is the one I think I put off. Yeah. And this one is what we just saw. Yeah. So let me do a quick. Yeah, it is. In fact, let me move these so that the summary is at the end. Okay. So let's open up the summary. Talk about the summary a little bit. And let me bring it over. There's our summary. Let me close these so I can see you guys over there. So, in conclusion, total resistance. The total resistance in a series circuit is the sum of all the individual resistances, R1 plus R2 plus R3, dot, 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 dot. In this case, there's 6 dots. But that means that, any other resistors that are in the circuit equals R sub T or resistance total circuit resistance. The same thing with the currents. Current 1 is equal to current 2 is equal to current 3 is equal to whatever if there's multiple paths, well, multiple places within the series circuit, not paths, but multiple places within the series circuit. You know, behind the first resistor, after the second resistor, after the fourth resistor. That's what that's actually saying. That is equal to the total current, or I sub T, I total. Current is the same in a series circuit. The current leaving the power supply flows through each device. And that's really important that you remember that. The current is always the same in a series circuit. Voltage, the voltage source. Voltage drop across resistor 1 plus the voltage drop across resistor 2 plus the voltage drop across resistor 3 plus the voltage drop dot, dot, dot on how many ever resistors you have in circuit. So the sum of the voltage drops across each device in a series circuit is equal to the source voltage. And like I mentioned, the largest voltage drop is across the largest value of the resistor in a series circuit. For example, a 100 ohm resistor and a 200 ohm resistor that are in series and connected to a 10 volt power supply, the voltage across the 200 ohm resistor will be larger than the voltage drop across the 100 ohm resistor. And like in this case, I can also say that 2/3 of the voltage is going to get dropped on the 200 ohm resistor, and 1/3 of the voltage is going to be dropped on the 100 ohm resistor. And I'm just kind of just going out there, just kind of saying that off the top of my head. But use a 10 volt source and a 1 amp current, and see if you don't get 6.66666 ohms. Volts on a 200 ohm resistor, and 3.333333 ohms. Volts. Sorry, on a 100 ohm resistor. It'll proportionately drop like that also. That's why when you have two resistors of the same kind or the same value, then it's half and half. That ratio still is there. Anyway, with all that being said, there is the lecture material. We'll have some labs, and we're going to talk about a decade box, which is basically a box that has, and you know, I haven't seen them in class. I'm not certain if we're actually going to get to do this one, but I'm just going to look it over. It's just a box basically that you can dial in resistors. You can dial in from 0 ohm to 99999. Sounds like a tax scheme of some kind. And we'll kind of adjust the values and the voltages, kind of what you were what you were doing last time. And then there'll be a wire series where it's pretty much the same thing. We'll get 6 resistors from 1K to 10K, and we'll put them in series and do some calculations. And let's look at this one, this other lab. This one just takes a single ammeter and puts it in the circuit. And notice that the ammeter is here. Well, what's the total resistance? What's current? The ammeter is here. What's the total resistance? It's current. This one's really a quick one. You move it over here, and that kind of helps you with the actual wiring of a circuit. So we've got that one that we're going to work at. Then this one is kind of like what we were working with, but pretty much the same thing. We're gonna put 3 resistors in series with a 10 volt supply. We're going to figure out the total resistance. We're going to find out what with the meter the current is on resistor 1, and basically it'll be like, okay, so what's the current here? What's the current here? What's the current here? It's the same as the current here. And then what those voltage drops are, we're going to be measuring those voltage drops. We're going to calculate them first and then measure them. This is another version of that. We're going to connect the circuit below, choose 3 resistors, replace R1, R2, R3. Those are the 3 resistors now, and we're going to complete the table that's below here. So is that it? Oh wait, there's one more. What's this one? Oh, this one has to. Oh, okay, I see. let's see. This one has us find 5 resistors and place them, you know, you've seen this, you've done the calculations, you've measured it, and then place the resistors in series, calculate the values, and I think we actually did this. This isn't asking for current, so actually this might be one from the previous one. But this is talking about total resistance, which, yeah, you guys did do this. So guess what? I am going to take that one out of there. And I'll actually just hide it so you can't see it. Anyway, any questions, perhaps? Ruben, do you have any questions? Anybody else have any questions? I noticed there's only 3 watching. Hey, we got 6 thumbs up. Don't forget to do a thumbs up, and like they say, don't forget to subscribe down there. You know, press that button so you can see when any of my other videos might come out too. That's a really good way to know when the lecture actually posts too. YouTube's been kind of weird lately. I've been uploading videos and the lectures even. You know, you would think that the lecture would be available immediately after, and it takes like overnight before it even shows up. So, but unless there's any questions, I probably have covered, you know, what we're going to do in the next lab next week. So feel free to send me questions via email.
Says, I'm good, thank you. It's like being in class an extra day.
Yeah, it is, Ruben. And actually, technically, you're supposed to be in class both days, but because of the COVID, you know, that's why. At first, they told me just do a video. Well, okay, I could do a video, put a video out there, but I thought, no, I'll just go ahead and I stream normally anyway. I'll go ahead and stream the lesson. And then if somebody wants to interact, ask questions, you know, I'm here, and it's a little more, you know, like class. Exactly. You know, you don't have to do it. You just, as long as you watch the video, hopefully, you know, the information will come through. Yeah, normally I would have been in front of the classroom doing this. So, and you know, I kind of miss that because there might be somebody else that asks a different question. You know, if not everybody is able to be here, then we might not get that variety of questions. You know, you might be fine with something, but somebody else might ask another question that they're not sure about. So, but anyway, with that, thank you for being here, Ruben. Thank you, everybody else, guys. You know, like I always say, live long and prosper. You know, no matter what you do everything just for fun. I think this has been a lot of fun for me. Hope it has been for you also. I'm going to go ahead and end the stream now, and then I'll go ahead and post the lecture if you want to look back at it, and of course so that, you know, so everyone else could also see it. So anyway, I'll have to do this with my left hand this way.